that if we have dynamic equilibrium for a system, that implies that the V center of mass stays constant. So that's right out of Newton's laws, but now we're applying it to a system. But if you let the dust settle, this is the equivalent of conservation of linear momentum. Both of these statements are identical. They come from the exact same place. And so what this is saying here is that systems must readjust themselves after a collision to keep. One way of saying it is that we keep V center of mass equal to a constant, or I can say equally that the total momentum of the system stays a constant. So it turns out that using conservation of momentum is a lot easier. And because it's a lot easier, we have, it's more mathematically appropriate to use this. So what this is really telling us is that if I look at the momentum of a system, initially, this equals to the momentum of the system afterwards. And this right here is what I would call the second commandment of physics, the first being conservation of energy. And the way we started looking at this is we started looking at elastic collisions. And when we looked at elastic collisions, we called these the perfect collisions. So perfect collisions only occur under extreme delicate situations, but they don't occur in everyday language. So why would we even study elastic collisions? Because it sets up a precedence of what is going to happen in an idealized situation. And we looked at 3 cases. And these are the 3 cases that we looked at. The first case that we looked at equal masses. And so when we looked at equal masses, what we saw here is that we had a block come in this direction. And it's going to collide with the second block. And the way we set it up here is we set it up that the momentum of this guy was 0. So in each situation, we always set the target, right? This is the target. This guy here is the projectile. We always set the target equal to 0. So then we looked at this situation and we said, if there are no other forces but the collision forces, then it tells us that the impulse, the external impulse is 0. So therefore, the total momentum of the system is a constant. And so then we start our before and our after situation. And what we found here is that in elastic collisions, momentums are exchanged. So what do I mean about a momentum is exchanged? Is that this block, the momentum of 1 goes to 0, and it transfers all of momentum 1 into block 2, and block 2 momentum transfers to block 1. So in other words, we now have a momentum of 2 final, which is equal to P1 initial. And so when we start to look at this situation, we get this situation where the momentums were exchanged. And so the way we looked at this thing is we drew a bar diagram. So if I look at a bar diagram, it says that all of the momentum coming in P1 initial is moving in this direction. All of the momentum of 2 was 0. So when I add all of these together, we find here is that this represents this constant. So these objects, blocks 1 and 2, have to readjust themselves to conserve momentum. So if this red bar is how much momentum is going forward, and 1 cannot go through 2, then all of this momentum has to be transferred to block 2. So the momentum of 1 transferred all of its momentum to 2, and as a consequence, the momentum of 1 goes to 0. There's an exchange. Then we looked at our second case. Our second case, we dealt with a massive target. And so when we looked at a massive target, what we found here is that in this situation, very similar to what we did up here, what we found here is that we had a very large block coming in. Let's say that this is the size of this block right here, and it's coming in with this much momentum. And as it's coming in, it's going to collide with a smaller block, which is this guy, who is again, the target is at rest. So according to conservation of momentum, if I identify this as my system and there's no external impulses, then the momentum must be conserved. So then what I'm seeing here is that, again, there is an exchange of momentums. And what I mean by the exchange, there's an exchange of momentums, and they adjust themselves to keep momentum fixed here. You know what? I drew my picture wrong. If I say massive target, 2 should have been big. So what I'm going to do here is that I'm going to erase this and I'm going to say projectile. My apologies for that. Okay. So I'll say that. So then what we see here is that what would we expect? So you could imagine that this was a bowling ball. And this is a golf ball. So we would expect that if I threw a bowling ball at a golf ball, that the bowling ball is not going to lose. It's not going to transfer that much momentum. So I would expect that the bowling ball will continue to move in the forward direction, which almost all of its momentum being retained. It's sort of like a Mack truck hitting a moth. So what would we expect a golf ball to do? We would expect a golf ball to move very, very quickly in the direction of the bowling ball. So if I look at this thing, physically, this is what we would expect for it to be like afterwards. So then if I go to a momentum bar diagram, then I start to draw something like this. So I imagine that I have this amount of momentum coming in. And as I see that, as before, this is 0. So immediately this tells me that the total momentum of the system has to be fixed again. So this has to be my total momentum line, which is a constant. So what would I expect? I would expect that most of the momentum stays with the bowling ball. Not all of it. It has to give up. It has to transfer some to the golf ball because the golf ball is now moving. So I would expect that it's going to have a little bit less momentum, and then a tiny bit of this is then going to be the momentum like that. So picture-wise, this is what I'm seeing here. And then our third case, we're going to look at a massive target, and we play the same game. So now what we're doing here is that we're doing what? We are now going to throw a golf ball at a bowling ball. So we could imagine that we now have a golf ball and we're throwing this at a stationary bowling ball, which again has a momentum of 0. And again, this is our bowling ball. So again, if we choose our system, we could see here that the only force acting on this is just the collision. So if I look at the before here, what do we expect to happen? What we expect to happen is that the golf ball is going to come back at effectively the same speed. So in other words, we expect the golf ball to bounce back with the final momentum that's approximately equal to the negative of what it came in. And as a consequence, the bowling ball should be moving to the right, and we would expect that bowling ball to be moving very slowly. So this is our after picture. So when I'm looking at this, the first question, and here's where the power of the momentum bar diagram becomes very, very, very powerful. So when we look at this, I play the same game where I say, okay, this is how much momentum is coming in. And so when I'm looking at this amount of momentum, once again, we have the same picture in each of the 3 situations. We have our total momentum constant line. And so now, because the momentum after the collision is in the negative direction, I have to draw this in the negative direction. So this one is now moving in the opposite direction. And we think that this will be roughly about the same speed or the same momentum afterwards. So then we started to think about what happens when a baseball hits a bat. The first thing that you got to do is that you got to bring the ball to rest. So this is the momentum here that is used to stop block one. Now I have stopped block one. Now I have to speed up block one to go in the other direction. And you could see that that momentum is one square. So now I have to then add another block, and this is to speed up block one. And therefore, this is the momentum of the bowling ball afterwards. Now, the reason why to predict this is really quite hard. Without a bar diagram, it's almost impossible to understand this. And what you're finding here is that there is a massive momentum going to the right with the bowling ball. In fact, the momentum of the bowling ball is much bigger than the momentum of the golf ball that came in. And what you're seeing here is it has to readjust itself in order to conserve that momentum. So even though it's moving very fast, the momentum of the bowling ball, which is 2F here, right? This is the bowling ball. That momentum is huge, not because it's moving fast, but because its mass is so huge, but its final speed is very small.